I'll be showing you how to use a lathe to machine a bearing holder. A bearing holder is a round indentation that houses a ball roller bearing, much like a pillow block. This particular chunk of aluminum is going to be a rear spindle for my son's off-road cart. So there'll be a bearing on each side and a live axle passed through. The first step is to locate the center of where the bearing will go, and in my particular case, is the very center of the whole block. The next step is to chuck the block in the lathe. Because my lathe was set up for a different job previously, I had to turn the chuck jaws around so they don't stick out enough to hit the cross slide. The block is then placed into the approximate position, and the live center of the tailstock is placed into the indentation that I made earlier, marking center of the bearing. Once the tailstock is extended, the block remains flat against the chuck, and I can tighten the jaws. It's important as the jaws start to hit the block that you tighten the other side as well. So this way the block is not shifted out of position. This way the boring and cutting is done from center that was marked. In order to give the lathe cutter clearance into the center, a hole must be drilled. This hole will extend through the block so I can center the bearing on the other side as well, so there's more than one benefit to drilling this hole. I started the hole using a center drill, which is a short, stubby, and incredibly accurate bit used for starting holes because they simply don't walk. Once the hole is started with the center drill, a regular twist drill bit is installed in the chuck, and the hole is bored all the way through the block. Here you can see the two pieces of the bearing, the tapered roller bearing itself and the matching cup. The cup is a tapered ring that the bearing rides in. It's made of hardened steel, so this way the bearing runs on this hardened steel rather than in the aluminum block I'm machining, which would wear out very quickly because aluminum is much softer than steel. This gives the design some durability. We will be machining the hole to a precise 2.430 inch diameter and a 5/8 inch depth, which is the outside dimensions of the cup. If I machine this accurately enough, the cup will have a friction fit in the hole and remain in place even if the bearing and the load that was on the bearing is removed. For machining operations like this, I always like to undersize the hole to start with, machining the diameter and the depth with repeated cuts, then do a final cut that takes off about 5/1000ths of an inch to the precise measurement that's specified in the design. This ensures a smooth finish and a precise fit. The lathe is a 1959 Atlas closing automatic lathe. It has several transmissions to control cutter movement as well as overall speed, allowing to move cutters slowly for a finer, better finish, as well as faster to hog out material quickly to reduce machining time. I always cut from the outside diameter inward towards the center. Doing the other way can be disastrous if you're not paying attention and do not stop the cutting action in time as it hits the outside of the diameter that you're machining. It's much easier to remove additional material than to add it back in. Now we're almost done. So the bearing cup, you can see, fits tightly, and the bearing sticks out of the block exactly as the design specifies. I have to cut a relief on the bottom because the bottom race of the bearing sticks through just a little bit, and that hole will be extended all the way through using a boring bar. That's not part of this video, but I just wanted to explain what that's about. Anyway, hope you enjoyed it. Bye.